It's 8:30 almost. Okay, but let's follow this thing slowly. Okay. So I have another thing called a TCP congestion window. We have two windows. There was the one that the receiver was advertising, saying how much the receiver can take, and then the congestion window, which is the sender is setting, saying what do I think I can safely send into the network without causing congestion. Okay, and at any point of time, the final window that you will use, which says how many packets can you send there without being acknowledged, okay, is going to be the minimum of those, which makes sense. Okay, I don't want to flood the, make the receiver overflow, nor do I want to increase the congestion in the network, basically. And congestion window is the one that is going to vary. So adjusting sending rate is nothing but saying that adjust the congestion window. And depending on, we'll see different events, because increase the congestion window, decrease the congestion window, and so on. So it's varied by sender, and congestion control, as I said, is a sender side task. Nobody else does anything. Whereas if you look at the flow control, which is what the receiver advertised window is dealt with, it's a receiver side task. The sender just uses that. Okay. So basic principle. Try to follow me, think with me here, okay? So on detecting packet drop or 3 duplicate acts, we'll see, you want to decrease the congestion. That is simple. Okay? On receiving act, which basically saying your packets are going through, you want to increase the congestion. All right? But the question is, how fast or how slow do you want to increase the congestion? So just think of this. Start from a network where you have no idea about what the congestion in the network. So you just opened a connection. Okay. Now, if you are very pessimistic and you say, I want to increase my congestion window very slowly. Okay, so that drops don't happen. So which means if your congestion window is 1, that is basically like a stop and wait. You are going to wait for the act to come back before you increase your congestion. So if you had a high delay link but high bandwidth link, that means you could have sent, the act will take a long time to come back, but then you could have sent a lot more packets then, so you're wasting it. Okay. Now fine, at the beginning you don't know, so you set 1. But then if you get that act, you're kind of probing the network to see what can the network take. Do you increase by another 1? Okay. Or do you increase by something else? What is the amount by which increase? Because if you go too slow, okay, then you are wasting the bandwidth. If you go too fast, okay, then you are going to clogger the network very fast, basically. Okay. So TCP congestion control, all TCP congestion control talk about 2 phases, slow start and congestion avoidance. And the names, the first name is kind of a misnomer. You will see slow start is not really slow. Slow is the one where I want, the slow start is actually the phase where I ramp up the congestion window quite fast, okay, if I keep on getting acts, so that I can go up to a certain point very fast. And then I say, maybe my luck will run out pretty soon, so let me now slow down. But initially I want to ramp up pretty fast so that at least I get a good congestion window fast. Okay? So which phase to do? That depends on a variable that is universally called SS threshold, slow start threshold. Okay? So initially you will always set congestion window to 1 MSS. MSS is a fixed quantity. Okay? You continue doing slow start until your congestion window is less than equal to threshold. Congestion avoidance when it is greater than. Some places you will see it's less than and greater than equal to, doesn't matter. Okay. So we'll see how we increase the congestion window, but if SS threshold is a fixed quantity, if your congestion window is less than that, I will follow the slow start algorithm. If it becomes greater than that, I will follow the congestion avoidance. Okay. So what is slow start? But before we go any further, there is something confusing here. If you read, or when I talk, if you read textbooks and so on, but that's how it is. Okay, so you need to understand this. So far, we have got everything in terms of bytes, and that's what it is. TCP is a byte stream. Okay. The advertised window we talked in terms of bytes. Sequence number we said byte for the first position. Acknowledgement number said next byte we expect, and so on. When it comes to congestion window, there is something that we talk and there is something that we implement. Underneath everything is bytes. But then I will talk in terms of multiples of MSS. So I will routinely say congestion window is 2, congestion window is 3. That doesn't mean it's 2 bytes, it's 3 bytes, it's 2 MSS, 3 MSS. But then when you go down to the implementation, your congestion window is 2 into MSS bytes. It is going to be the minimum of 2 into MSS bytes and the receiver window. So as before, TCP is everything about bytes, so your implementation of congestion window is about bytes. Okay. So it's actually when you implement, your congestion window is actually 376 bytes. Okay, so it won't be 300 more than that because 536 is the minimum this thing. 700 bytes. But when you talk about increasing congestion window, etc., etc., you will say 1 MSS, 2 MSS. So you will routinely just say 1, 2, 3, 4, 5, 6. Okay. So this is something that students find confusing. It's implemented as a number of bytes. Our most description will talk about in terms of number of segments. Actually, I do not know of any textbook anywhere which talks in terms of, it says increase the congestion window from 700 to 1400 or something. It's increase from 1 to 2, basically. And a segment will mean a full size segment. Okay, so this is 1 MS. Otherwise, there's a question of if I say increase by 1 segment, how much is a segment basically? Because we have seen segment size can vary. And at RSC 2581, which is the first one that talked about it, not the first one, I think. Well, the one that kind of first good one that talked about it, okay, talks in terms of both space time. Okay, so remember this. There are various implementation of TCP congestion control, which differs mostly in how and when congestion window is computed. Okay. First one we'll do is TCP Tahoe, which was the first congestion control protocol in internet, and then TCP Reno, which is the next extension. Is very old, 1990, but if you look at implementations now, name-wise they will differ, but everybody will have slow start, congestion avoidance. It's just the formulas for adjusting the rates and all, which will vary most. There are some other things, but you will still have slow start, congestion avoidance, free duplicate acts, on timeout, you do this, and so on. Okay. So, in my defense, if you look at almost any textbook, any slides on the internet with a basic undergraduate course, you will not see anything beyond TCP Reno. Just a bit of history. So, okay, this is not 63. This should be 1983. Sorry, 63 there was no internet. So ARPANET will switch to TCP in 1983, and then internet suffered that congestion collapse I was talking about in 1986. So there was initially no congestion control algorithm. Okay, and again, if you are in network, you will know Van Jacobson is a very, very famous name in networks. So he fixes, so he was the first one to give this slow start congestion avoidance congestion control algorithm. So fixed in 1987, around that. Okay. And it had 3 things: slow start, congestion avoidance, which is still there, and something called fast retransmit, which is also still there. We'll see what each of these things are. And then in 1990, so extended with fast recovery. So 4 things that we will do when we talk about congestion control is slow start, congestion avoidance, fast retransmit, fast recovery. Okay. Of which actually slow start and congestion avoidance are the 2 phases. And again, I use the SS threshold to decide which phase I am in. Okay. Okay, so let's start with slow start. As I said, it's used to find a good sending rate initially at startup or while recovering after congestion. Okay. We'll see more details. The idea is this: whenever you are starting traffic on a new connection or when you are increasing traffic after congestion was detected. Okay. So this one is this line, whenever increasing traffic after congestion was detected, I will modify rather than on a timeout basically, because as I said, congestion can be detected either by timeout or by 3 duplicate acts. On 3 duplicate acts, we don't always go back to slow start. But right now I'm doing TCP Tahoe. TCP Tahoe will always go back to slow start. We'll see basically. So here is what slow start is. You initialize CWND to 1, that means 1 MSS. Okay? And each time a segment is acknowledged, you increase by 1. Okay? And you continue until any one of these 3 events happen. Either you reach SS threshold, in which case you will switch over to congestion avoidance, or you have a timeout, or you have 3 duplicate acts. Okay, on each of these what happens, we'll see. So you see, it's called slow start, but just for simplicity, think that every segment is act individual. There is no cumulative, just for second. Okay? That means you send the first one, you got the first act, CWND becomes 2. Now you can send 2 segments. Now then you send those 2 segments, the 2 acts come back, CWND becomes no, because for each of those 2 acts you will increase by 1 and you already had 2. So it becomes 4. Now you can send 4, you already had 4. Okay, each of them is kind of an exponential increase. So that's why nobody knows why it was called slow start. Okay, you are supposed to start slow rather, but you are kind of being aggressive to at least get to a point so that you don't waste too much bandwidth. You want to get to a point very fast. Okay, what is that point? That will be determined by SS threshold. Okay, but then what is SS threshold initial? You don't know. You have no clue either. Okay? So just keep that question in mind. So slow start, as I said, is not so slow. Okay, you have 1, you have 2, then it goes to 4, then it goes to 8, and so on. In practice, it won't grow that fast. Okay, because you know. So think of the packets going, segments going smoothly. There was no timeout, nothing basically. Timeout, something else will happen anyway. Okay, so you will usually have, remember your act sending rules. You will have delayed acts basically. So for every 2 of them, you will send 1. Right? So this increase in the congestion window by 1 is on a per acknowledgement basis. It does not matter how many segments that acknowledgement is acknowledged. Okay. So if you have 2 for every 2 segment 1, then rather than increasing the congestion window by 2 for 2 segments, it will get increased by 1. Okay. So in practice, it may be slightly slower, but at best, if everything works okay and so on, and the acts do come back properly, okay, then you are going to have a very fast increase still. The still increase is not going to be linear. It's still going to be exponential. It's just going to slow down the exponential. So this is just something to note that change in congestion window is per act. So a cumulative act will still increase the window by 1. So these are the kind of things that you should work out. Take a SS threshold. Suppose you say, I send 1 act per 2 segment. Okay. Or take an SS threshold to be slightly larger. You work out how many RTTs you will need for it to reach the SS threshold. Because otherwise, when you are sending those 2 packets, assuming RTT is larger than transmission time, okay, you are actually increasing, you are doubling every RTT. RTT is round trip time. The first one comes back is 1 to 2. Then you send the 2 packets, comes back in the RTT 2 to 4. Then you send the 4 packets, comes back in the RTT 4 to 8, and so on. Okay. Okay. So no timeout skill, just suppose, so it goes on basically. So on slow start, we got to a SS threshold point. We'll see how to set the SS threshold. Okay. So slow start sets a good congestion window fast. Okay. But then you slow down the congestion avoidance by entering the congestion avoidance phase, the increase. As I said, again, what is that point? What is the SS threshold point? That you have to kind of estimate. Okay. But beyond a certain point, you say, oh, my luck has favored me so much so far. Let me now slow down now. But I still want to increase. because maybe the network can take it. Or maybe by the time, so that's the other thing. It's not that you are sending a file, for example. Okay, when you are sending a file, you are going to send a file and then be done with it. So maybe you will get lucky and you are increase it. Before it actually hits the timeout, your file will be over. Remember, it's a per connection basis. It's only for that connection that is sending, not over everything over the thing basis. Okay. इधर ही घूमना है इसको. तो दादा এখান থেকে যান, আওয়াজ হচ্ছে. Okay, so what is congestion avoidance? So if it is greater than SS threshold, then you do this. Then you basically go back to a linear increase. Okay, you say increment congestion window by 1 by congestion window for each segment is acknowledged. That means if you have a congestion window of 4 and you send them out, then in one RTT you will get back 4 acts. For every act, you will increase by 1/4, which means over one RTT, you will increase the congestion window only by 1. But this is where you have to remember the thing. Okay, so 1 by CWND doesn't, what does it mean? Okay, it's 0.25. It's actually 0.25 of whatever the number of bytes is basically, is the current congestion. That's what you are actually implementing underneath when that act comes. Okay. So basically your congestion window is increased by 1 only if all segments have been active in the congestion. No timeout here, so you are being able to send. Moment timeout happens, something else happens. Okay. So it increases by 1 per RTT versus doubling per RTT in slow start. So this is what is called additive increase. Okay. With me so far? Online, can you hear me?
Yes, sir.
Okay. So this one, if you see, so this is kind of your RTT. So you have congestion window equal to 1. First one is you got 1 act, 2. Then you send 2 of them, comes back. You don't make it 4 anymore. You make it 3 on. Then you send 3. All these 3 comes back. You make it 4. Then you send 4. All those 4 comes back. You make it 5. It's kind of a linear increase now, basically. Okay. What happens when you have a detect a congestion? So first look at timeout. Okay. I'll talk about 3 duplicate acts a little later. So what does a timeout tell me? A timeout is telling me that I have gone too far. Okay. So I need to set my congestion window back. Not only that, now that my congestion window back, maybe my SS threshold I should reduce also. So this is just a formula which has worked well. So what I do is SS threshold is set to half, not the current SS threshold. It is half the current congestion window. I'll have an example short. So my congestion window has increased to 20, let's say. SS threshold may be, I may have been already in congestion avoidance. SS threshold may have been 16 or something. Okay. So I don't want to go to 16 by 2.8 because I have been able to go to 20. So I'll go to 20 by 2.10. But that's just the SS threshold. That's not the congestion window. That says when will my slow start again, stop again. Okay. The congestion window, so this was one of the problems with TCP Tahoe or even Reno for timeout. I will be very drastic and set it back to 1. Okay. But I will have slow start to ramp it up fast again, but not up to that level because somehow I feel it's kind of a very conservative approach which says on a timeout, okay, you reduce that the congestion window drastically to 1 again. You start from beginning and you don't go that far basically because that far may have been too far. Let me show you a picture and you will understand. And you enter the slow start phase again. This is what is called a multiplicative decrease. See a picture. So this is, understand this picture pretty well. This is when I'm just starting the connection. I have no clue about what the SS threshold is. Okay. So I will set my congestion window and SS threshold to the same. Okay, some default. Let's say I set it to 16. Okay. There are two possibilities. 16 may be too high or 16 may be okay. Okay, but I'll set it to a high value, not very low. Okay. Then I will start the slow start and it will kind of be an exponential increase. If this value is really high, before I enter the congestion avoidance, I will have a timeout. Okay. When I have a timeout, I can say basically that this is how far I could go while I'm kind of probing the network to see what it can take. Rather than probing it slowly at the beginning, I probed it very fast. And I found the network can take up to 12 with its current traffic in the other place. Okay. Moment that happened, I'll drop my congestion window down to 1 again. And my SS threshold, I'll set to whatever the current congestion window by 2. Now I got a kind of an estimate of what the network is. My network can take 12. Okay. So I will go fast up till half of that and then go slow after that. Okay. So then I start doing congestion avoidance, which is a linear increase. Okay. So I could have gone up to 12. Okay. But let's say out here, I got this thing. I could have gone anywhere actually, not 12. Okay. So there is no upper limit for the congestion avoidance. Okay. But then say a congestion window equal to 8, I again get a timeout. So these are the timeouts. It's not increasing because nothing is coming down. It is flattened out. Okay. So now it says basically the network condition has changed somewhat. So 8 is the maximum it can take. So I'll drop it down to 4. But I will always start back with congestion window equal to 1 and just on a time. So the basic idea is very simple. I probe the network very fast, but only up to a certain point. Okay. So that I have some good amount of packets flowing in the network. And then I kind of probe it slowly to see where I can go. So I get an increase, but then if I'm unlucky, I'll get a timeout. But if I'm lucky, before the timeout occurs, maybe my traffic will be over anyway. Okay. What do I do on 3 duplicate acts? So my 3 duplicate acts basically tell me that it's a total 4. So first one, first the 3 duplicate ones. It's telling me there is congestion. There is probably a packet lost. As I said, it's not 1 or 2 duplicate acts, it's 3 duplicate acts. So 3 is my too many. But some packets are going through. So I should not be that pessimistic about it. Okay. So first thing I will do is I will retransmit the segment, that missing segment, without waiting for time. Okay. Why is that? Because this is telling me that there are 3 other segments that are actually sitting on the receiver's buffer. Okay. Assuming that they have not been dropped, potentially sitting on the receiver's buffer. So if I can send the missing segment fast, okay, it can actually complete the entire and move my congestion window if the application takes it and so. So the assumption here is basically that your receiver advised window is always larger than the congestion window. Otherwise, the receiver advised window will be your bottleneck. So whether your congestion window is low or high doesn't really matter. Okay. So you retransmit the segment first of all. You set SS threshold to congestion window by 2. Okay. But the congestion window you don't set to 1 anymore. You send to congestion window by 2. Again, by 2 is just something. Okay. You say that some packets are going through, it's not that much congestion, so I should not get down to 1. Let's not be that pessimistic. Okay. Timeouts is saying packets are dropped, so everybody is clogged. So let me send very slowly so that the router has some chance of clearing up the backlog. But this is telling the clogging is the routers is not that much. Once in a while, something is getting dropped. Okay. So I reduce my congestion window but I do by 2. But then I do a plus 3. Why do I do a plus 3? Obviously something to do with 3 duplicate acts. Okay. What is the plus 3 for? Why what is the rather what is the intuition for plus 3? Huh? At least 3 which are yes, you are on the right track. Let me say. So, what was the congestion window telling you? It's telling you you can send this many segments, or this much bytes in terms of that, so this many segments, maximum segments. Okay. Now, you think of it this way, that 3 of them are already sitting there. Okay. If they have been dropped, I have to send them again. I don't know, maybe they have been dropped. Okay, but I'm assuming the receiver buffer is larger. So 3 of them are sitting there. Okay. So I can artificially inflate my congestion window by putting another 3 out there. Because out of my window that I'm thinking, 3 have already gone. None of them are acknowledged. But 3 have already gone and sitting there. So maybe if I'm lucky, if I send the missing one, okay, I don't have to send those 3. The cumulative act will come for the entire thing. And then I will advance my congestion window out there, or my receiver window out there. Are you with me? I don't know. I'm guessing. Okay. See, the fact that duplicate act means something is missing. That means something is there after that. Okay. Potential. Now, when you get out of order packets, as I said, most TCP implementation will buffer it as long as it can. Okay. And as I said, the implicit assumption here is that the receiver advertised window is not the bottleneck. So you're absolutely right. Just because I get 3 duplicate acts says something is missing, okay, but it does not say, but when do I say duplicate act? Because something has gone there. That's why you send the duplicate act. Okay, so it was there in the buffer. Now if something else has come and I had to drop something, and then my policy for dropping which one, maybe all 3 are not there yet and so on. Okay? But for every duplicate act, it is saying that something else is reaching there. Okay. So I'm guessing they're sitting there, and if I send the retransmitted, the missing one rather, I will be able to fill that. Yeah. Let's put it this way. Rather than saying before receiving acts, okay, you say before, yeah. So the acts will change the condition window. It will increase the one. Okay. Yes. Right. Now, the sender side limit is the number of bytes in terms of congestion window size into the MSS size, maximum segment. Okay. Let's say that comes to 3000 bytes at this point. Your receiver side window is, let's say, 5000 bytes. So which says you can send only 3000 bytes up to what? Okay. When you get the act, your window will increase. Okay. So now see the receiver side thing. Okay, that you already know. The congestion window of the 3000 is going to, so if there is no timeout and the act comes back, you are going to increase it with something. The congestion avoidance, then will become maybe 3300. Okay, if slow start, it will become 1 MSS more and so on. So now it says basically, subject to the receiver advertised window again, the mean of that basically, I can keep on sending this many bytes, new bytes, basically. Okay, these are the number of bytes that I can pump into the network basically. So if you recall that picture, congestion window equal to 1, you pumped in 1 MSS, 1 segment. Okay, now think that the actual segment that you sent may not be an MSS. Okay, so you may have sent less. So that much in your credit now, basically. because underneath the implementation is in terms of bytes. When it comes back, when the ACK comes back, the size increases. Okay, if everything keeps on coming back, the size increases. Suppose there is no timeout, no duplicates or anything, it will eventually become equal to receiver advice window, and then the receiver window will start controlling your flow basically. Yeah. No, what? Come again? I didn't get it. Oh, so that's what I said, the confusion. Okay, when I say minimum of CWND, okay, you don't think so. CWND is 3, doesn't mean you take minimum of 3 and that. 3 multiplied by MSS. No. Which is the other factor? MSS is fixed, right? Receiver window is that coming in the window side, window thing in the header. Yeah. Yes, but you don't know. That's the thing. Think. It's a network. The biggest problem in networks and in distributed systems in general is that you have to work with what you know and what you can probe to get. You do not know exactly what is happening. And the worst problem is, just a general problem in mathematics distributed systems harder, is that to probe it, you have to ask something somewhere. By the time the answer comes back, okay, your thing will have changed, basically. Okay, you don't know. But what the duplicate ACK is telling you, the virtue of the fact that the duplicate ACK was sent means the packet has been received, which says packets are getting. So 3 duplicate ACKs, I'm optimistic that all 3 are there now. They have reached, at least all 3 are there, because they are individual packets. Yeah. Can be. Okay, but those what those are telling me, whether those 3 are out of order or not, I don't know. Okay, any out of order packet will send you an ACK. We saw that. What it's telling me is that something is missing, because the last ACK I got is ACK 1000, which says up to 999 I have received, and I am keeping on getting ACK 1000, ACK 1000, ACK 1000. So something is missing after that. Now 3 of them has reached after that. Maybe I have sent 5. Okay, which 3 have reached, I don't know. So there can be missing gaps there also. Okay, but anyway, doesn't matter, because I have to first send this. You don't send selective things in TCP, basically. Online people, are you okay with this?
Yes, sir.
Okay. So this is just what I said now. Okay. So this was TCP Tahoe. TCP Reno added what is called a fast recovery. So TCP Tahoe basically did this. So fast recovery basically is on 3 duplicates that you go back to congestion avoidance. Don't go back to slow start. Okay. And so to say what is done, mostly fast retransmit and fast recovery are always implemented together. Okay. So to put them together as to what happens on 3 duplicate ACKs, you do this. The first one, retransmit, set SS threshold, this already we have seen. Now, just think with me. So now you've got 1 3 duplicate ACK, you have done this. Okay, timeout changes everything. So no timeout yet. Okay, now you keep on getting subsequent duplicate ACKs. What is that telling you? That one more packet has reached. Remember, there is no timeout. Okay, just think with me here. Okay, so last ACK I got was ACK 1000. That means up to 999 has reached. And now I'm keeping on getting duplicate ACKs. There is no timeout. Okay. So if there is no timeout, okay, then nobody other than that 1000 onwards missing segment is getting retransmitted. Are you with me? On the 3 duplicate ACK, I retransmit the missing segment. Okay. Anything else I retransmit on a timeout. If that particular segment does timeout. There is no timeout yet. That means the only thing that is getting retransmitted is that 1000 to that missing segment. Are you with me? Yes, no. That means every duplicate ACK that reaches there is indicating a new packet that has reached there. Right? And it has reached there, it has been placed in the buffer at least once. So therefore, I am sending the ACK. So now I will be optimistic and say that means by the same principle of that class 3, I'll increment by class 1. There is one more out of order packet which is just waiting there for me, so that if I put this missing segment, this entire thing will become. Maybe not. Maybe because to place it there based on my policy, I dropped something else there. But usually, it's common sense that if you got missing segment 2 and then you got 3, 4, 5, 6, 7. Now when 7 reaches, you're not going to drop 3. It doesn't make sense. You're going to drop 7. And if you don't have place to put 7, you will not send that duplicate. Are you with me? And one more thing will happen. If you don't have place to put 7, okay, what else will happen? So, exactly, okay. So, all these duplicate ACKs are actually indicating they are actually in the buffer, okay, because otherwise my receiver advertised window will keep on coming down with each of them and will eventually reach 0. Now, there are details here, because again, as I said, what happens with out of order packets is up to the implementation. So, you may send the duplicate ACK, then wait for a very short time. If the missing segment does not come back, you say drop it to free up the buffer space. But at least at the time of sending the duplicate ACK, the packet must have been placed in the buffer. Which means I will be optimistic out of the congestion window. Okay, if I say I can send 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 2 has not gone, but 3, 4, 5, 6, 7 has now gone. So I'll say, let me send 2 and 9, 10, something. 1. Are you with me? The intuition as to why do I do a plus 1? Okay. But then, if I get a new ACK, what is that telling me? So I was getting ACK 1000, ACK 1000, ACK 1000, ACK 1000. Suddenly I get ACK 5000. What does that tell me? So it is complete. Okay. Now I will set it to SS threshold. The congestion rate. SS threshold is again, you could have done SS threshold by 2, by 2/3, whatever. Okay. I'll actually reduce. So this is very funny. As you keep on getting duplicate ACKs, saying that one missing segment, you are kind of being optimistic that all these other things are waiting. So in anticipation that this I'm retransmitted this one and it will reach, I'll complete this thing, I'm sending some more things. But moment I got the ACK, I'm saying, oh, this much is completed. Okay. Now it is back to the normal case. Okay. Look at an example to understand how these values are changing. It's an example I borrowed from somewhere because it's beautiful. I could have drawn it, but I could not have drawn it better. So this is the beginning of the condition. Okay. So this is your slow start. You go all the way up to here. Okay. Then you go to congestion avoidance. You set SS threshold to 28 by some means, whatever. Then you go to congestion avoidance. Okay. Here you got a 3 duplicate ACK. So in this entire picture, there is no timeout. Okay. Timeout is simple. Timeout you do congestion window equal to congestion window by 2, SS threshold, sorry. SS threshold equal to congestion window by 2, congestion window equal to 1, go to. So timeout is kind of a hard congestion. You say your network is clogged already, okay? So you want to send very slow. You go back to your congestion window equal to 1. Okay? It's only what you are doing on 3 duplicate acts. Okay? So this will be your new congestion window. Why is this? So you see you are at 36. Okay? So 36 by 2 is 18 plus 3 is around 20. Okay? Then you keep on getting duplicate acts. So you have a linear increase of 1 per act. Then here you got the act for the retransmitted thing. That will be a new act. Okay, at least some more has been reached. Okay, then you reduce your congestion window down to threshold, but then you start in congestion avoid. On a timeout, you used to start in slow start. So there are two things. In a slow start, on a timeout, I get my congestion window to congestion window by 2. Okay, SS threshold also I need to, sorry, again I'm confused. Sorry, on a timeout, I set my SS threshold to congestion window by 2. Okay, my congestion window to 1, and I go on a slow start. I could have also set congestion window to congestion window by 2 and then slow start also. But the intuition was the network is clogged. So you want to pump very slowly. You want to probe the network very slowly. Okay. Here the difference is I don't change the SS threshold. Okay. I change the congestion window to whatever the SS threshold is. Okay. Oh, sorry. SS threshold also is changed, right? Yeah, congestion window by 2, my question. So it's the same as normal time. SS threshold is changed to congestion window by 2. So congestion window was, okay, here is where I did not change the congestion window. Okay. Let me go back. Go slow. 3 duplicate acts, you change the SS threshold. Okay. But then on every subsequent duplicate act, you don't change the SS threshold. So on this 3 duplicate act, my SS threshold got set to 18. Congestion window is that plus 3. Congestion window by 2 plus 3. Okay. Then I change this. My SS threshold did not change. Neither on a duplicate act nor on a new one. But it's already been reduced by the first 3 duplicate acts. Now that I got a new act, okay, I will set my congestion window to SS threshold, which has already been half from the earlier SS threshold. Okay, and I will enter the congestion avoid. Yeah. Let me just finish. Sorry. Okay. So the idea is on a timeout, I am being very pessimistic because network is already clogged. On a 3 duplicate act, and when I got a new act also, what is that telling me? 3 duplicate act is telling me there is some congestion. Okay. So as long as I get some more duplicate acts, there is some congestion, but it's not that much because packets are still going through. A new act is telling me that maybe it has cleared up a bit, maybe more new acts will come. So I'm not as pessimistic as in timeout case. I set my congestion window to SS threshold, okay, which is already the earlier congestion window by 2, okay, and then I just start in the congestion avoidance phase itself. I don't try to slow start, go back to congestion window equal to 1. Yeah, go ahead. No, that, see, what you send will depend on what act you got. When you got a new act, are you talking at the end of getting a new act? Once you receive a duplicate, you keep on sending the missing segment. Nothing. Okay. So there is one. I went back and read the RFCs yesterday because I had a doubt while telling you this in class, basically. I'll confirm again. So I spent quite some time on it yesterday. I forgot actually. So this thing that I told you, I will confirm. So when So I told you that if there was a segment missing, okay, and there's a retransmission. So if you had a 100-byte segment that you have sent, okay, and then the ACK did not come back or whatever happened. So when it timed out, when you will retransmit, if there was another 100-byte available, you will send the entire 200 bytes. That's what I told you yesterday. Okay, I'm going back on that 99%. I still have that 1% doubt. I will check. So once you send a segment, you decide by Nagel's algorithm what is the one that you're going to send. Once you send a segment, you set a timer for that segment, and then you're going to only transmit that. Retransmit means that. So if something else is available, that will be another segment. You're not retransmitting only one. See, congestion window is just telling you how many bytes you can transmit. If you have bytes available in your send buffer, and the window, that minimum of congestion, this says you can send 1000 bytes, Nagel's algorithm will kick in and send whatever number of segments that can be. Yeah. Retransmitted one is the only one that is there, basically. I get your question. I'll think more about it. Maybe I'm not being very clear, basically. Yeah. Right.
Assuming that the sender is sending at the max rate of the congestion window possible, and ACK is being sent without a cumulative at every element.
These are two different things, okay? The first assumption is there is no assumption that the sender is sending at the MSS rate. It's per ACK. The actual segment that is going out need not be of size MSS. But the congestion window is increased by that. Okay. So I get your doubt. Okay. So you have only said 100 bytes. Why should you increase it by 1000 bytes? Right. You are kind of saying, because that's the problem with this, basically this confusion between MSS congestion window being talked about in terms of number of MSS, and then underlying it's a minimum of bytes and that basically. Okay. See, if it increases too much, your receiver advertised window will kick in, and you will not be able to send anything. But it's kind of saying that I sent 100 bytes. Okay, it did not have, because at routers and all, your packet processing is dependent on the header. Okay, why are you your buffer clogging up? Mainly because your router is not able to process packets fast. Okay, now I agree with the size of the packet, there is still you have to store it, you have to put it from the input buffer to output buffer, you have to pump it out and so on and so forth. But the time that primarily goes is on the header processing. And the header processing time is the same whether it's a small packet or large packet. But I'll go back and check and so on to confirm what I'm saying basically. But it's increased always in size of multiple MSS. But then that does not mean every segment that you send out, that will be determined again by Nagel's algorithm and everything. If you don't have enough thing to send, so your sender sent you 100 bytes. Okay, by Nagel's algorithm, you will send it the first unacknowledged one. Okay, when the ACK comes back, your congestion window will increase by 1 MSS, which may be much larger. But the sender has not given you any data. The sender gives you another 100 bytes. You cannot wait till the MSS, basically. Okay. This is why I left it for the end. This is probably seems simple, but because of this 1 into byte business and other things, and this actually, we're just doing a first level network course with a lot of stuff and so on. Congestion control has been the area of extensive research and all, because it affects many other things. Because see, you are taking a local action. Okay. But then, unlike flow control, which dealt with sender receiver and you have a connection established, you can get any more information between them. Okay. But you are basically just trying to do your bit to reduce the congestion in the network. But then, if you were sending only 100 bytes per second, just suppose, just think for a second. and somebody else was sending 1 million bytes per second. So it's that person who is clogging up the router, not you. But the effect of both of them is a packet drop, and both of them will go by to one MSS and then one MSS, two MSS, three MSS, and so on. Ideally, you should not have to go back at all, right? So there's a fairness issue also. There's a lot of other aspects to this congestion control thing, but overall this has worked. Basic idea wise, this worked pretty well. Because intuitively you say you don't know, you first try to be optimistic, get up to a point, then don't try to push your luck too much. Slowly. Maybe if you try like this, don't be too greedy. I could have continued with slow start. Maybe I would have finished before any congestion happened. But exponential is a very fast thing. Are you with me? So in conclusion, TCP you will kind of see sawtooth behavior. It's a classic TCP sawtooth curve basically. The beginning, initial slow start. Okay, you let it continue. You start with a high SS threshold, kind of probing to find out what is the optimum point. Then you go down to 1, then slow start, congestion avoidance. Then this will be your duplicate acts, fast retransmit, fast recovery, and so on. Somewhere out here you will have timeout, then you go down to 1 again, and again slow start, again this thing. But again, if you have estimated your RTTs and everything, but there's a lot of mechanism working in the back. Moment you have a timeout, okay, remember Karn's algorithm is there. So your Karn's algorithm will kick in, your timeout will increase. So these things are not too often. It's usually, once in a while something gets reordered. Even 3 duplicates are not too often, basically. You will usually get everything out. But then again, congestion can happen. I forgot your name, Aditya, right? No. You don't know Nikhil. Ho. Satvik, sorry. Satvik Chapai. I remember everybody else's name in this row, man. Okay. So I'll think about your question. I get your question. I'll think about it. Okay. But the thing that I'm trying to let you know that congestion window just tells you what is it that you can send. Okay, what you send will be now determined by Nagels and your timeout and all those things. This is just saying this is the maximum number of bytes you can send, minimum of this and the receiver advice. So you don't overflow the network, you don't overflow the receiver. And finally, the last slide of TCP. There are many implementations of TCP. Some to address some problems of Reno in the early days, some suited for specific scenarios, links with high bandwidth delay product. Okay. They're called long fat links. Okay. Long because the delay is large, fat because the bandwidth is large. Okay. There, if you increase slowly, okay, if you go down to congestion to 1, even if you do, your RTD time is very large. So if you have large bandwidth and the RTD time is very large, that means you're wasting more bandwidth. So you want to ramp up fast, but then again you have to worry about that if you ramp up too fast. So basically they will differ with your when do you enter, how do you set these parameters and so on. But just to give you a flavor, there's a lot of new things. TCP Vegas was very interesting work. As I said, it's one of the only one that I know of. I may be wrong, but the only one, the really famous one that we know of, which uses delay as one of the things. And still there with Linux and all. So Linux and all, you can choose which congestion control algorithm you want. You don't want to do that, okay, unless you know better. But you have, there are multiple options basically. And many of these other ones like fast TCP, AGS TCP, TCP big, okay, they were all basically because see, when TCP was developed, RTT was high But then the internet was not this widespread. Okay, so links were not long. They were slow, but they were not long, basically. Second thing was the bandwidth was very low. So even if you take a little bit more time, and there was not enough things to send also. You had very text-based simple things. No, it is funny. Okay? So it was okay. You were thrilled with something really working and doing this thing. But even then you understand, even then you had a congestion collapse in 1986. Okay, because it was exploding like anything. Okay? But then many of these higher ones, because the bandwidth have increased tremendously, you have very long links and so on, very long high-speed links, basically, spanning the world and so on. Many of them were improvement on that. So you don't need to know which one is what and so on. I just wanted to give you a flavor that, what was the history. So what you study mostly in almost, why almost, all textbooks that I have seen, almost all, again, all undergraduate network courses that I have seen over the world, okay, call it whatever, wherever you go, will stop at TCP reading. Because as I said, you still talk about slow start, congestion avoidance, because where you do that, how do you change things and so on. Duplicate acts, fast retransmit, fast recovery, standard things. So that completes TCP for us. Okay. So if we just want to go back and summarize, you have the basic properties of TCP. Okay, reliable, blah, 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 blah. Mark them. Okay, you should know them basically. Not a question of mark them, you should know them by heart. Easy. You have the TCP header. For the purpose of the exam, remember it. IP header, TCP header, Ethernet frame header. These are three headers, UDP header. Okay? At least the more important fields. Nobody is going to say whether there is the third field or fourth field or something, but remember that you have fields like that, so that if you are asked to do things with it, you know that, okay, I can utilize that field and so on. Okay? Then you just think about every part of TCP. Reliable. What do I need to make it reliable? Retransmit. So when do I retransmit? How do I set the time? Okay, when are at set? Okay, everything to do with that. Okay. Flow control. You already know that, but ask, yesterday's class was good basically. So you ask yourself many questions. Why did they do it this way? What was this thing? Some of the parameters you cannot explain. They are very empirical parameters. Okay. But why suddenly, why not go like this in congestion control? And then congestion control, remember basically everything slow start, congestion avoidance, fast retransmit, fast recovery. Okay. This one is not in the syllabus. Any questions first of all? Anybody? Online? Are you following? I have not written anything today also. I spent a lot of time to put pictures on the slides yesterday. Online people, are you okay?
Yes, sir.
Okay. Any questions? Anyone? Okay. So done with that, we'll take 5-10 minutes more, 5 minutes more. What's the time? 9:25. Okay, so 5 minutes max. I want to talk a little bit, just pointing out things to you. This is not in the syllabus, will not be asked in the exam or something. Okay. So this ECN thing, explicit congestion notification. As I say that ideally I want to know about congestion building up in the routers before it has settled, before it starts dropping. Okay. So basically you want to know what is congestion. Basically you have a queue in the router, you put packets in there and the queue gets full. When it gets full, you start getting packets full. And then after some time, waiting for the timeout and all, even afterwards, it knows about it. Ideally, it would be nice to have, say that a router can, if the router can indicate to me okay, that my queue is 70% full. Okay, some threshold or something. So something that by which the router can say at least I'm getting congested. Okay. But then packet is going through the router. Router can always create queue. Okay, router can always detect that it's getting congested, but how does it tell the sender? It's not worth, it's just not feasible to send a packet back from the router to the sender all the time. Okay, the router has other things to do. Okay. So what the router does in ECN, it sets a flag in the header of the IP packet when it forwards. But what flag is there? You don't have any flags for ECN. But remember, you have the type of service flags, which I have said not many people use, almost none. So when you implement ECN, ECN takes some bits of those TOS, 2 bits actually, to say these 2 bits are ECN bits. And there are some codes for that. Okay. But then the packet, just think with me here. The packet is going from sender to receiver. It's in the router on the way to the receiver. Fine, it sets the packet on the IP header. The IP header is not going back to the receiver, to the sender. Okay. So how will the sender know? Because eventually the sender has to reduce the sending rate. Right? So we'll go to the receiver. Think of it as receiver. Okay. And then the receiver will send an acknowledgement. And then the receiver will send, when he sends the acknowledgement, okay, he is going to set some weight in the TCP header. Because when it comes to the sender is not going to see the IP header. It's just an application of TCP header. Why I'm saying this, okay, you will see, is that so you start with this idea that would be nice to have the router indicate congestion. But to make it work, you go from concept to concept. You said, so fine, I have to say, tell the sender. Router cannot tell the sender. Who can the router tell easily? Receiver. The receiver can tell the sender. That's all conceptual. But you've got a scheme. Now you think, so how will the router, now you go to the how. How will the router tell the receiver? Cannot modify the data. Can have the receiver that thing only. Then you say, oh, TOS fields are not used. Let me take out 2 fields. Then you go to TCP header. Okay. And in the TCP you say, TCP header, again there is no field for ECN. So I have to cut out some fields. Okay. So suppose I do that. Does it work? Okay, this is my offline class. I can keep on looking at your eyes until you answer, basically. Not you. Okay. Online, you can just sit quietly, as these other people are doing. But this is fun. You see why system design is fun. So you have to work with what you have, but then make it happen. Okay. So what is the problem? Remember, you are sending to somebody. The receiver is in somebody's control. You are in somebody's control. So think about the receivers or even the router's IP processing fee. The router will have to know that to use ECN, right? The receiver will have to know to interpret those 2 bits. So first of all, I will must have everybody ECN capable. Okay. But then how do I know my receiver is ECN capable? Good. I can negotiate many options during connection establishment. Okay. So all these things, maximum segment size. Okay. Your maximum segment size is basically, default is 576. But if you have 1500 byte link, why will you send 536 byte data? You will negotiate. And then the receiver will say yes. Same thing you will return the AC. But you see, in the internet, routers are under different people's control. Receiver is with somebody, sender is with somebody. The same receiver will connect with so many senders and so on. Okay. So assuming that everybody will do ECN is not a good idea, even though there's a lot of ECN capable things out there. Okay. But by default, it will work without ECN unless you really want to probe and so on. But then again, this is not in the course or anything. Okay. But you always try to look at your, when you do design a system, always try to look at your environment. You see, what do I know? What can I control? What additional information I know? ECN is used a lot for congestion control when you run TCP in data centers. But then you have a set of machines which are all under your control. You can configure them whichever way you want. So there are data center TCPs, there are different variations of them. But one of the things, the way you know the congestion in many of them is by these ECN. So you can make it work. Everything is under your control. You can make everybody capable. So the protocols that we study in general in a first level course is broadly, you need to know about the internet things around you and so on. But then when you take it somewhere else in some other domain, okay, you may have additional things out there that are, you may have additional problems also. Okay. So suppose I take this congestion control algorithm, okay, and I put it in wireless. You have not studied wireless, but in the basic idea of wireless. Okay, there are hop by hop things, you transmit radio transmissions and so on. If there are still links, right? Would it work well? I'll give you a hint. Think about detecting congestion. How did you detect congestion here? Drop. Forget the 3 duplicate act for a second. Detected drop. Okay. So, what is your implicit assumption when you said drop is an indication of congestion? Based on what you studied so far. Why can packets be dropped? Tell us all the reasons why can packets be dropped when you go a path. Anything else? Don't forget AFP की short test one दे दिया. Don't forget basic communication. So you can get just corrupted, right? That's another reason why it can get dropped. There can be other small reasons, but at least look at that. Okay. So the implicit assumption is that the loss due to corruption and all damage is not as high as the loss due to drop router. Take it to wireless, that's no longer true. There's going to be a lot of interference and all because now it's unguided medium. So now you may be unnecessarily pumping in packets when the cause of congestion is something different. So plain TCP does not work very well in wireless. It does work. And then the access point is not just the only wireless. But you think of wireless, the chance of packets getting corrupted due to other reasons rather than congestion at the intermediate nodes increases. So all I'm saying is that it's not just for network, it's for anything. Operating systems you take. Okay. So you have studied round robin scheduling. Yes. Okay. So time sharing, etc. What is time sharing? It's not a trick question, it's an easy question. Good. Okay. But then always think implementation. So when you have to write in the exam, you can say everybody assigned a time quanta and this. How will you assign the time quanta? What's a good time quanta? When you code, you cannot say choose a good time quant and leave it to the system. And don't tell me machine learning will learn. Okay? But there is a point in there. No, I'm not saying it's full joke. Okay. So how will you choose the time quant? What's the time quant in Linux? Order 10 millisecond, 100 millisecond, 1000 millisecond. Huh? 5 to 20. 5 to 20 microsecond time quantum. You will die of context switching. Okay, it's in the order of, okay, this is a little bit old information, but I don't think it has changed too much. It's in the order of like 100 milliseconds or something. Okay. I'll check because it's said 5 to 20 microsecond. Okay, I'll check whether it cannot be, because unless your machine is extremely fast, you have extremely fast time and all, context switching will kill you basically. Okay. But I will check, caution. Okay. But in milliseconds is possible, it can come. But then, how to determine that? When you are building Linux, you are building a general purpose OS. Okay. Why do you do time sharing? Because you want to run interactive applications. Okay. If you don't want to run interactive applications, you will not do that. So, you have to choose something. Okay. And you make a choice which is, over empirical studies on what everybody feels okay and so on. But if you had a system, remember there's an operating system in everything. It's just the scale varies. Your routers is nothing but basically a processor and an OS. Cisco has Cisco IOS, which is specifically designed for network based. So when you know your tasks, what are their requirements and all, you will not do time sharing, or even if you do time sharing, you will adjust your context. Basically. So always think about your system, that what does the system have, what additional information I can have over my text. And exam questions are, again, this time I will be very lenient probably. Okay. But don't smile too much. Very lenient is a subjective term, But see, when you say machine learning, okay, so how do you know these parameters? Okay. So you set something. How do you know it's good or bad? Lots of time you are shipping a product, you set a parameter. But you don't know always in what circumstance it's going to be used. And the same parameter may not work for some. So here's another technique. It's going to watch your systems use for some time. You'll watch what is the typical job run time. What is the typical memory usage? What is the typical this? And you can have adaptive algorithms there. So at the beginning, you will have a bad performance while you're collecting data, but then it's going to adapt your parameters. Which is exactly what your RTT estimation is. I could have put a RTT of 50 microseconds, but then it's going to run on fast networks, slow networks, it's going to run everywhere. You kind of watch your system, you adapt. It's classic example of that. And that now offline machine learning is becoming an important technique. You kind of, sometimes some parameters are easy to see. Some parameters of the usage of your system are sometimes hard to see. So you collect the data and you run learning techniques on them. Okay, talked enough. Okay, so if you have any questions, ask. Otherwise, end of class. Meet next Monday again. So we have UDP. Then we'll probably do one application layer protocol. I'm not very enthused with it. Just to give an example. And then we'll do DNS and DHCP, things that we see. There will be one last class, not in the course, that I'm going to talk about RF. Okay, thank you. Any questions from online? Okay, if there are no questions, class is dismissed. So I'm going to close the meeting maybe in 1-2 minutes.